Electrophilic addition reactions. Addition reactions are characteristics of unsaturated compounds. Depending on the mechanism, addition reactions are classified into electrophilic, nucleophilic, and free radical additions. Usually, electrophilic additions are given by alkenes and alkynes. For example, addition of halogens to olefins, addition of hydrogen halides, hydrogenation, hydroxylation, hydration, etc. And in such reactions, the rate determining step involves addition of electrophile. Let us see the electrophilic addition reactions of alkanes. In olefins, the carbon-carbon double bond consists of a strong sigma bond and a weak pi bond, and as pi bond is weak, lesser energy is needed to break a pi bond, and the pi electrons are more polarizable. When the electrophile approaches the alkene, the pi electron cloud attracts the electrophile, which is electron deficient, and forms a pi complex. Addition of halogens to olefins. Chlorine and bromine adds to olefins at room temperature to form vicinal dihalides, that is 1,2-dihalo compounds. For example, when ethene is treated with bromine, bromine is reddish brown, we get 1,2-dibromoethane and the product is colorless. Similarly, when bromine is added to propene, we get 1,2-dibromopropane. And this addition of bromine to unsaturated compounds, it's a test for unsaturation. So when bromine is added to an unsaturated compound, there will be immediate decolorization. And in the case of saturated compounds, there will be no decolorization. Now let us see the mechanism of addition of bromine to olefin. It's a two-step mechanism involving a cyclic bromonium ion. In the first step, bromine gets polarized in presence of the olefinic bond, and the positive end of bromine molecule form a pi complex with a double bond. And this pi complex rearranges to form a cyclic bromonium ion, and the formation of this cyclic bromonium ion is the slow and rate determining step. So if we consider the addition of bromine to ethene, so bromine molecule, it gets polarized in presence of this ethene, and pi complex is formed such a way that the positive pole is pointing near the pi electron cloud. And this is the pi complex. And this pi complex now gets converted to a cyclic bromonium ion. In which Bromine carries positive charge. And in the second step, the Br minus, which is the nucleophile, gets added to the cyclic bromonium ion, and we get the final product, that is 1,2-dibromoethane. Addition of hydrogen halides to olefins. Alkenes form addition compounds with halogen acids. For example, when ethene is treated with HBr, the product is bromoethane. And the order of reactivity in electrophilic addition is Hi, then HBr, and least reactive is HCl. And this is also a two-step mechanism involving a carbocation intermediate, and the formation of carbocation is the rate determining step. In the case of symmetrical alkenes like ethene, 2-butene, etc., symmetric means with respect to the double bond, the groups present are identical. In such case, there is the possibility of formation of only one product. In the case of unsymmetrical alkenes, addition of halogen acid can take place in two different ways. For example, if we consider propene. When HCl or HBr is added to propene, there is the possibility of formation of two chloropropane and one chloropropane. And experiments show that 2-chloropropane is the major product, along with 1-chloropropane as the minor product. And the addition of unsymmetrical reagents like hydrogen halides to unsymmetrical olefin is governed by Markovnikov rule. The rule states that when an unsymmetrical reagent like hydrogen halide is added to an unsymmetrical olefin, the negative part of the reagent goes to the carbon containing lesser number of hydrogen atoms. And this rule, it's an empirical rule based on experimental observations. So in this case, propene, it's an unsymmetrical olefin. So when HCl is added, according to Markovnikov rule, negative part of the reagent Cl minus gets attached to the carbon containing lesser number of hydrogen atoms. So 2-chloropropane is the major product according to Markovnikov rule. Markovnikov addition is understood if you look at the mechanism of addition of HBr to propane. The electrophile H plus adds to the double bond in the slow step to form a carbocation intermediate. So HBr first ionizes to H plus and Br minus, and the electrophile H plus approaches propene, and the addition of H plus to propene is the slow step, and that is the rate determining step. And in this case, there is the possibility of formation of two carbocations. One is a primary carbocation which is less stable, and the other one is a secondary carbocation which is more stable. And in the second step, Br minus gets added to this carbocation, and we get the final product, that is CH3, CHBr, CH3. That is 2-bromopropane. And that is the major product, or that is the Markovnikov product. And the product corresponding to the less stable, and this is the fast step. Product corresponding to the less stable carbocation, that is CH3, CH2, CH2Br, that is 1-bromopropane. And that is the minor product. So Markovnikov rule can be explained by considering the stability of the intermediate carbocation. The product corresponding to the more stable carbocation will be the major product. Anti-Markovnikov addition. When HBr is added to unsymmetrical alkene like propene in presence of peroxides like benzoyl peroxide, 1-bromopropane is formed as the major product, which is contrary to Markovnikov addition, and this reaction is known as anti-Markovnikov addition or peroxide effect or Kharasch peroxide effect. And peroxides get converted to free radicals easily. So the mechanism is free radical addition and not electrophilic addition in this case. So addition reaction of HBr to alkene in presence of peroxide follows free radical mechanism. The bromine radical adds to alkene, and the product corresponding to the more stable free radical will be the major product. That is why we get the anti-Markovnikov product. And this peroxide effect is observed only in the case of HBr addition to alkenes, not in the case of HCl or HI addition. Reason is, in the case of HBr addition, both steps are exothermic in nature. Now let us see the mechanism of this Kharasch peroxide effect. The peroxide linkage, it's a weak linkage. For example, if you consider a peroxide, this compound is known as benzoyl peroxide. And this peroxide linkage, it is a weak linkage. When such compounds are exposed to either light or heat, it breaks into free radicals. So in this case, it breaks into a free radical, and which further breaks into phenyl radical. So the first step, that is the formation of free radical, phenyl radical. And this phenyl radical abstracts a hydrogen radical from HBr. So that bromine radical is formed. And this is the initiation step. And the bromine radical formed then undergo homolysis with propene, resulting in the formation of two free radicals. One is a primary radical. So when Br dot gets attached to propene, one possibility is formation of this primary radical, and the other one is a secondary free radical. So when bromine radical gets added to this carbon, we get a more stable secondary free radical. And in the second step, this free radical in presence of HBr, we get CH3, CH2, CH2Br, plus another bromine radical. And this is 1-bromopropane, which is the major product. Along with, we get 2-bromopropane, as the minor product. So peroxide effect can be explained based on the mechanism. Here it is free radical addition. First step is formation of the free radical. Here if you start with benzoyl peroxide, the free radical formed is phenyl radical, and the phenyl radical abstracts a proton, so a hydrogen radical from HBr. We get bromine radical. So bromine radical adds to propene. We get two intermediate free radicals. One is a primary radical and the other one is secondary free radical. And we know secondary free radical is more stable. So the product corresponding to the more stable secondary free radical is the major product, and that is 1-bromopropane, along with a small quantity of 2-bromopropane is formed.